Alright, here's our game Tilt. You move your character around a ever-changing maze and attempt to get to the top right of the map to increase your score by colliding with this flag. Here we go. You can see here there's a timer that counts down, so you can't just be idling around or else to set you back to the start. And there's also the score counter that increments every time you reach the top of the game. And as you can see, there is collision with all the walls in every direction. Yeah. You can see the score incremented. Yeah, stop that. So we added an additional mode. As you can see here, I am colliding with all the walls. But if I flip this third switch here, I will die when I collide with the walls. Right. But the game is still beatable in this mode, although it is harder. There we go. So as you can see, though we do have to reprogram the FPGA to do this, we can very easily scale the image and change the number of horizontal and vertical lines. And you can also see that it scales the flag according to the box size. Yeah, game is still perfectly functional in this state. And the timer also gives you less time the less number of lines you have on the screen.
Hi guys, this is Thomas Young, and I'm here to walk you through how we made the maps for Tilt. So first up here, this parameter specifies how large we want the map to be. Currently we set it to 420 by 420 pixels, but we can easily change that to whatever we want, up to 640 by 480. And then here we have the size of the boxes of the individual grids. So right now we currently have it set to make it to be a 7 by 7 grid map, and then we just set the default line widths to be 2 pixels wide. And then down here are the two generating functions we used to generate the horizontal and the vertical lines, the top being horizontal, bottom are the vertical. And then we also have down here, we have these four are the outer perimeters of the map, colored in white. So currently I have it set up so that no matter how the user decides to, how big the user wants the overall map, the map to be, as well as how many grids, everything scales accordingly with these parameters: the left bar, right bar, top bar, bottom bar. And then the flag also scales. Depending on how big the maps are. So this way we always have the flag somewhat center in the top right grid. And that's it on my part. Thanks guys, bye.
So as Thomas mentioned, the vertical and horizontal lines are configurable, and these are done through these generate functions that take in parameters that are set above. And all they do is set the initial position to whatever you set it to, and then add the length of the bars and the width of the bars to the final position, the x, y, and x2 coordinates here. And then these vertical and horizontal lines are controlled by two different random number generators. And these are courtesy of the Bomberman and Balloons group. However, we did modify them by adding new cases of 36 and 49 length bits. This allows us to control 6 by 6 and 7 by 7 grids. Going back to the map, and in this always block, the random HR register latches on to the random numbers generated by these random number generators, so that the horizontal and vertical lines turn off and on to create a different maze every second. These random number generators are also set to 2 different clocks. That way they are not, or although they are repeating the same pattern, they're repeating it at a different frequency and are latching at the same time, which gives the appearance of random numbers. And this snippet of code we use using a for loop. We iterate through all the different lines, and depending on whether this particular bit of the random number is a 1 or a 0, that line is either drawn or not. And the same is done for the vertical lines.
Hi, my name is Thomas Barrette. This is an overview of our collision detection code for our project. So we start out with an always block, always at pause edge, refresh tick. Refresh tick happens 60 times a second. It's synced up with our VGA display. So our first statement here is an if statement. It detects collisions with the outer wall by our player. Here H-min is the left edge of the player. L bar is the left wall of the maze. If the left edge of the player is past the left wall of the maze, then a collision has occurred. It's the same for the other edges. It's pretty straightforward. Down here, it's a little harder. We check for collisions with the maze walls. So we have a bunch of walls. They're randomly generated, so some are off, some are on. So we have to loop through them. So we have a for loop to do that. We only check if the wall is on, which is this if statement here, if not random HRK. And then this statement here detects if there's a collision. It's rectangle to rectangle collision, which is a pretty common algorithm for 2D games. It's pretty straightforward. The same thing for the vertical walls. If you go down here, we have an if statement. If there is a collision, the timer resets and the player goes back to the start. And that's only if the hard mode is on. Down here, we have 2D collision, which is for our easy mode. And 2D collision allows us to stop the player from going through the walls, just stop their movement. They can still like slide on the walls and bounce off them and stuff. So here, it's very similar, except we split collisions, collision X and collision Y. And we also, our if statement looks a little bit different, because now we check where the player is going to be. We check their future position at the next tick if we were to add their velocity. So if we add the velocity in the X direction to the left edge of the player, are they passing through one of the walls? And if they are, we set collision X to 1, and same for collision Y. Down here, it's the same, but it's 2D collision for the outer walls. Very similar statement. Our easy mode is on, then we allow collision X and collision Y to influence our movement. So we only allow the player to move, we only update their position if collision Y and collision X are equal to 0. So if collision Y is equal to 0, then their new position is their current position plus their Y velocity. But if collision Y is 1, they don't move in the Y direction. So you can hit a wall and then slide off it because the collisions are separated. And then if we're in hard mode, if there's nothing we don't stop them when they hit a wall because they just reset. So
Hi, I'm Connor, and this is how I got the accelerometer to work with the FPGA. After 2 unsuccessful attempts, totaling to about 8 hours, I found David J. Marion's YouTube tutorial and GitHub repo that allowed me to get the SPI master interface to work. The accelerometer runs at a 4 MHz clock and outputs data at a 1 MHz clock. In order to read information from the accelerometer, we need to read from specific registries in it. To do this, we need a 93-state finite state machine. The first half of this finite state machine totals to basically getting the accelerometer in measurement mode. Once it's in measurement mode, we wait a delay for about 10 milliseconds in order to begin reading from the registries of the X, Y, and Z data registries. Because we don't need the Z data registries, we actually don't end up using that data. There are 16 bits for each data registry, but we take 1 sign bit and 4 data bits in order to tell whether it's positive or negative and how big it is, so that it makes a difference based on how much you tilt. It then returns this data in one big list. Using the sign bit that we extracted from the registries, we use them as a ternary operator to tell Verilog whether the data is positive or negative. Because we're reading from the middle of the registry, and it's in 2's complement, when it goes into the negatives, it actually becomes a maximum of 15. That's why we have 16 minus the movement data. This corrects that issue. We also have 2 dead zones so that the player is able to move the block more precisely in order to solve the maze.